For the analysis of truss in ETABS, I use the example 3.2 from structural analysis by R.C Hibbeler. Here is the example 3.2. Determine the force in each member of the roof truss shown in the figure. The dimensions and loadings are shown in the figure also. State whether the members are in the tension or compression. We have to also find whether these members are in tension condition or in the compression condition. For the modeling of truss in ETABS, I have created the grid. You can see 1, 2, 3, 4, 5, 6, 7 grids in the x direction, 1, 2, 3 grids in the z direction, or you can say y direction. But in ETABS software, the vertical axis is the z axis, and this 1.1547 meter you can find by trigonometric method. So similarly 2.31 meter, and each base truss members are 4 meter, 4 meter, 4 meter. So the joint distance is 2 meter, 2 meter, 2 meter, 2 meter, and 2 meter. Before analyzing the truss in the ETABS, we should memorize our basic concept that truss members are connected together at their joints only. Truss are connected together by frictionless pins. The truss structure is loaded only at joints. The weight of the members may be neglected for the analysis, but in the actual in the real situations we cannot ignore that weight of the member, but just for the study purpose we ignore the weight of the truss members. So now we will move for the modeling of the truss member in ETABS. Here I am opening my ETABS software 2016. It will take some time. Now I will start from a sketch file. You can start new model from here and also from the file, new model. Model initialization. There are 3 settings. So for you can use user default settings. So I am moving from the scratch file, so that's why I am clicking use built-in setting with my problem is in metric SI system, so that's why I will select metric SI unit system and steel section database. If you are designing, then that's it's important. You whether select FPS system or SI system section database. Steel design code, that definitely for design purpose, that is concrete design code. I am clicking OK. Now here is a grid option, so I will again go back and check how many grids. In the x direction 1, 2, 3, 4, 5, 6, 7, and in the z direction 3, 1, 2, 3. So here number of grids in the x direction 7, number of grids in the y direction no need, so that's one is okay. In spacing in x direction is 2 meter, in the y direction again is not needed. I will discuss why I am putting in the y direction 1 meter. When we do analyze problems in our classes or in theory classes, we use XY system, but in software the horizontal axis is X and the vertical axis is Z. So I will put that is the vertical axis in which number of stories. So basically there are 2 stories and story height is 1.1547 meter first story, and second 2.31 meter. 1. 1.1547, and the that is the bottom story height, and the typical story height for the rest of stories, that is 2.31 meter. Okay, now I am clicking grid only. Okay, here now you are seeing two windows, 3D view and plan view. So I will just click, I will close one window. I am good to work only in one window. Elevation 1 apply. So here you can see 1 2 3 4 5 6 7 grids in the X, 1 2 3 grids in the X direction, and you can also check 1.1 here, 1.1547, and here. If your grid is not according to your conditions, you can also go to edit. In the edit grid story data, here you can also modify the grids. So here I am clicking close. Now I am going to define material properties. Material, there is already defined 50 grade steel. You can check its strength, that is 344 megapascal. Okay, for section, there are many sections. Here we'll just use a steel section whatsoever, because we will just use for the analyzing purpose. Here 31 whatsoever. Okay, now I am going to draw the truss members. From here, draw members. From here I will select any steel section, for example W250, and start drawing these truss members. Let's see. First of all, base members, from this to this, this. Okay, I am putting escape, or you can also click right click. Now it's just looking like that our truss. Now I am putting the boundary conditions. On the right side there is a roller support, and on the left side there is a hinge support. So I will remove these extra supports. Click these joints. I am going to assign joint restraints. So there are three options: fixed support, hinge support, roller support, and no support. Here I clicked apply. So now their supports are removed. I am going to click here. There is a roller support. Apply, and there is a hinge. There is already a hinge. Clicked apply. That will replace. Okay. Now I will apply the loads. On this joint and this joint there is 3 kilonewton, and on the vertical there is a 2 kilonewton. So in the assumptions we have taken that the self weight will be ignored, so that's why I am deleting the dead load. Yes, and I will consider only live load. So now I click this joint and this joint and assign joint load data force in the downward direction -3 kilonewton. Okay, apply. You can see. Now I will click this joint and apply -2 kilonewton load downward. Apply. 2 kilonewton, 3 kilonewton, 3 kilonewton. Here. Now Now the software do not know whether these are the beam members, column members or the truss members. To make these all members the truss members, we have to ignore the moments at the joints. For that purpose we have to make the members axial members. So I am clicking all the members. Here you can select all the members. Here I have selected all the members. I am going to assign frame, release or partial fixity. Here I am releasing the moments. Apply. Now these all the members are acting as axial members. Now I have assigned the loading conditions, support conditions and the members. Now I will run the analysis. Before running the analysis I will save my model. Here problem example 3.2, save. After saving the model I will run the analysis. Here you can see, now you can also see the deflections due to live load at any point. Here it's the vertical point 314 millimeter downward. Okay, you can also check the what are the units of the displacement. So the units of displacements here, if you are not showing, then click here. Here length units are in millimeter, so all units are in millimeter. Okay, now I want to see the reactions. I will go into the display, spot spring reactions. Here I will click all these, apply in the tabulated form or in whatsoever. Here in the left side that is the 4 kilonewton and in the right side it's a 4 kilonewton. Fx is 0. So what are the here? That is exactly matching our the theoretical problem. So now we will check the forces in the members. So in the software in FGB is 3 kilonewton compression. Where is FGB? FGB 3 kilonewton compression. So now we will see the forces in each members. I am closing it. Display forces. Here click on axial force. I am going to apply here. Now you can see that is the minus 3 kilonewton compression. Right click here, minus 3.007 kilonewton compression. Now we can see the forces in each members. Here in the vertical minus 4, and all the bottom members are in tension. So that's how you can model any truss of unlimited number of members, of unlimited number of joints in ETABS, and you can analyze with more accuracy and with more appropriate method. So that's all we have verified. So now we can also check one more member, for example FBF 1.73 kilonewton tension. FBF, this is a member 1.73. This is a member here 1.73 tension. So that's verifying our theoretical results. So that's all. Thank you.